All right, we're rolling. Let's go. We're going to talk about dynamic memory management. So this is kind of the deep stuff around pointers and memory allocation. This stuff took me a while to figure out. So I'm going to try to give it to you in a way that, maybe you can get there a little quicker than I did when I was first starting to code. We've definitely done a little bit of work with pointers. We started you out in Comp 130 for those of you who took that from me. And so we'll be reviewing a little bit of that stuff. We're going to definitely go deeper. And our puzzle homework assignment, which is coming up, will definitely involve a lot of memory and pointers. And so will the homework assignment after that. So we're going to get a lot of exercise on this stuff. So the lecture today is not really long, but it is kind of dense. So I'll try to take you through it slowly and not burn you out too quickly on it. Um, I've extended homework 4 by a week. Now I know a lot of people worked hard and some of you over the break to get this in. So I'm going to give everybody +2 points if you get it in tonight, and that's your final submission, just as a thank you for working over your spring break. It wasn't how I planned it to go, but it just seems like we just need a little bit of extra time. And I don't blame anybody for not spending the whole break on that particular assignment. So thanks for those of you who did, and hopefully that didn't ruin your break, and you got a little bit of time to work with. Now, I can't push the rest of our homework assignments out because the semester would get longer, so we still have to kind of hurry up and get on to homework 5. But hopefully I can help people get through this. Just reach out to me this week if you need some help on your blackjack homework assignment there. Okay. So today we're going to deal with dynamic memory. We're going to create for our lab today a triangular matrix. This is a really important data structure that you want to know how to make in C++ because there are a lot of really interesting math problems that don't need a full 4x4, 8x8, etc. square matrix. So a lot of matrices are symmetric across the diagonal, and so no point in wasting memory. But most programming languages don't have a triangular matrix. So we're going to try to make one in lab 17 using dynamic memory allocation. And then we will move on to creating something a little fancier in lecture 18. We'll talk about classes and we'll introduce this idea of a destructor. So you don't have to worry about that too much today. Today is just about allocating our matrix. So 2 weeks, regardless of the extension, unfortunately, we still have a quiz 5 and then our homework 5, which is our jigsaw puzzle, which hopefully you will find somewhat visually fun to do. So we're going to be loading up some mathematical descriptions of puzzle pieces and making an image puzzle. And we're going to be building that sort of in dynamic memory. So that'll be coming up in 2 weeks. So that a lot of that you'll be able to jump right into after our lecture today, but especially after our Thursday lecture, you should have everything you need to do to go after that. Now, just putting this out there for folks who just, are like, I just can't get on to blackjack right now. Homework 9 is still out there. If you really enjoyed working with maps, you can still come back and work on homework 9 instead of homework 4. It's just another homework out there. And remember, we only got to have 7 good homework grades. So you'll have 9 things to choose from all semester long, more or less, to sort of get a reasonable grade for the course. So let me know if you have any questions about that. But those kind of that one is not due until like the Monday before final exam. So you can kind of leave that one out there all the way till the end. But as many of you know, that's usually the worst time of year to be doing extra stuff. So choose wisely your strategy. Just want to give you lots of options for kind of getting the grade that you want to get. So just a quick look at what we have left now that we're just sort of back after the break. So we're going to be looking at homework 5 and, dynamic memory. That's going to be this week. Next week, we will do a little more on dynamic memory and we'll review this idea of const and introduce these 2 new kind of qualifiers for memory in C++ called static and mutable. Those are just little modifiers on things that we already know. And then we are going to get into what are called smart pointers. And this is going to introduce what we call an idiom or a pattern in C++ that we see all over the place. And we'll talk more about that when we get closer. It's sort of like pointers at the next level, and in a good way, right? So we'll actually be doing a Facebook homework assignment. We're going to simulate a pretty big program to simulates what Facebook might be doing behind the scenes using this special library called Smart Pointers. So we'll introduce all that to you. And then we get into inheritance. So this is something we've never really talked about before, but a lot of C++ development uses kind of like inheritance, like we inherit traits from our parents, our biological parents. So classes can inherit traits or data members from their inherited classes, so their ancestor classes. So we will begin looking at how we do that and why we would do that when we want to design software. And then we get into a little bit more on some corner cases, lambdas and functions and exceptions. And then we're going to do threads. Threads are really fun, I think. We all are lucky these days. Everything except our phones really have multiple cores in them. So these computers that we are dealing with in class here today have 12 or 16 cores, and they can talk to each other. But we've never really written any code that takes advantage of that parallelism. And so we're going to learn how to write threaded code in C++, which is a very cool and advanced thing. We don't usually cover that in a class like this, but it's gotten so easy to do. So we have some fun practice problems and labs and a homework for actually doing that. So our final homework is not maze, sorry, it's actually threads. So we'll actually do some threaded restaurant simulation where we actually simulate the operations of a restaurant. So I got to come back and update this slide over here because these are a little bit out of date. So those are kind of what we have left. And if we have some time, we'll just sort of review and talk about kind of high level subjects, what are called software patterns in C++, try to introduce you to some terminology. But I think we'll probably be pretty full with the stuff that we got there. But that's just a little look ahead so you kind of know what we have left to cover before the end of the semester. It's going to come pretty fast, I think. And then our final exam, I don't think it's Tuesday. I actually think it's Thursday. I got to double check and see. So it's changed over the last couple semesters for some reason. So I think we'll see that out on our Thursday. Okay. But that's just kind of a look out there. Let's take a look at some code to just jog our memories, especially after the break. And feel free to click into any of the links here if you want to see some live code. But remember that a pointer is what we call a compound type. So if I have an integer, that integer has an address in memory whether I care about it or not. Everything that has a name has an address. So there's our variable name A, and it has an address. And even this variable here has an address, right? We might not know that it does, but it actually does. So, but when I declare PTRA, the type of information it's going to store is an address, and it's an address of an integer. So that's what we mean by a compound type. Our data type is two things. Yes, it's a pointer, but it's what kind of pointer? It's an integer pointer. So when I read code on data types, I kind of read from the left or from the right to the left, pointer to an integer, okay? So we'll see lots more examples of that today as we go. But if I want to pull the address of something and pull it into another variable, we said we just use this ampersand sign. So give me the address of the A and store it over here, okay? So now we've kind of pulled the address of A over there. And if I want to say what is at that address and sort of follow that address to this location, we use our little dereference symbol there, okay? So two different ways to use the star, one as part of a compound type and one as an operator, almost like a function or a mathematical operator. And unfortunately, those two things kind of have different meanings, and I put different colors up there to help you on that. But we just have to look at the context of the code and how we use it to really understand what's going on there. Okay. So those are the two first very important parts of that. So when I do that, of course, I'm following the address that's here to get to this thing and pull out the 5 from that. Okay. So we say that PTRA points to 5, but really we just know that we're just storing the address, and C++ follows that address to get the information we want there. Okay. So it's just a little indirect lookup. Okay. Now, if we're on a 64-bit machine like a phone or any modern computer, that's going to be 8 bytes wide. That's 64 bits. So if we were on an Arduino, like stuff we use for little mini projects, that might be 16 bits architecture. That means our addresses can only have 16 bits, maybe, or 16 bits as opposed to 64, right? So there are different architectures, and it depends on how sophisticated the computer is. But all of our computers and our phones and everything these days have 8 bytes, which is the same as 64 bits wide. Okay. So let's take another look at this. So here's our integer again, 4 bytes wide, 32 bits, right? So I can put a 10 in there, or I could put something even much bigger than a 10. Here's my pointer over here, 64 bits wide. So of course, I'm just pulling the memory over there like we saw when I say PTRA equals the address of A, okay? So that's the get address of kind of operator again, just in a different kind of a layout here. Now, what if I wanted to use that address to store something in A? So I can say star PTRA equals what's in B. Now, these have to be apples and apples. So B is an integer, right? PTRA is a pointer to an integer. So that's not apples and apples. But when I dereference PTRA, what I'm saying is go to what you're pointing to, and that, of course, is an integer. So we really do have apples and apples. That's an integer, and that's an integer. And that's the only reason that we can move the 15 over to the A, okay? Because when I dereference a pointer, it basically takes away one of the stars, right? It takes away that star, and we essentially are back to an integer over here. So the system seems a little confusing, but you can pretty much trust that it's always going to work out once we figure out the rules. We can follow the rules. It's a very bulletproof, very well-defined system that ensures that we're really only copying similar things between similar places. Now, we could find ways to force the number 15 to go into here. That would be very bad, because we don't know what's at address 15 in memory, right? So C++ is going to fight us every step of the way to prevent us from putting a 15, which is an integer, into an address variable. We can do it. There are ways we can force it to happen, but it's not a natural thing. And modern programming languages try to stop you from doing that unless you really, really, really want to do it. So, and for the most part, we won't really try to go that direction. Okay. So that's our dereference operator for storing things over there. And it's not going to let us just do something like put an integer in PTRA, right? It's just not the same type. So we're not going to be allowed to do that. So on a bigger scale, whenever we do stuff like this, all we're really doing is saying, pointing to things. I used to think that in memory somewhere there were these arrows. I was like, what, where are we storing these arrows? Well, we're not storing arrows, of course. We're just storing the addresses, and we talk about them like they're pointers, okay? So today we're going to go deeper on this stuff. We're going to talk about how C++ uses the memory in our computer. So there's really no free lunch. Somewhere someone had to figure out how to use all these transistors in our really modern computers and our telephones. And if you're writing code in C++, there's a fairly consistent organization to how a C++ program arranges its memory. So one of the areas is called a stack, and that's really anywhere we have a named variable, which I always use blue for. Those things go in this area of memory called the stack. The things that we use the new keyword for the majority of the things that we do that are dynamic, will go on an area called the heap. And we will see next week what static memory is like. But these are our three primary areas of memory, okay? So when we have a dynamic array of something, it's always going to be comprised of some fundamental data types or instances of classes that we've already actually created. So we're going to look at four different ways to do that. And if you can master these four exercises, you will really have a handle on dynamic memory management in C++. So they're kind of simplified exercises, but they're like anything. It just teaches you the building blocks of this. And that will take us right into a good understanding of what you need for our next homework, which is homework 5. Okay. So we're going to go through these today and, one by one, even though they look kind of boring and simplistic, the syntax is going to cover all of the kind of stuff you'd use for most of your programming lives. But let's look at a kind of pulled back picture of what a program looks like in C++. Even though they call it text memory, sort of a misnomer, it's all of the zeros and ones that literally are your compiled program. So when the compiler reads your text, your main.cpp, and every other CPP file, it mushes them all together into an executable file on the disk. And then it loads that file into fast memory. So the disk or the long-term storage on your computer stays good even when the computer's powered down. But the RAM or the random access memory is always cleared when you power down your computer. So when we load up a program to run it, we're loading it up into random access memory, and it goes into this area called text memory. All of our variables that we're using in some current scope are active, and we call that the stack. So as you may guess, it is very much like a stack, like the stack that we learned about a few weeks ago. So all of our variables when we're in a function are right there on the top of the stack available for us to use. The variables that we are kind of were behind us in some other scope that we were in are possibly buried on the stack beneath us or have already been popped off if we've kind of left that scope. So our stack is called a stack because it quite literally is a stack of variables, and it's always going to have the stuff that's in the current scope defined by our curly braces available for our code to use. Now, this other kind of memory we're going to start exploring now is the heap. So this is like this crazy playground. It's like the Wild West of memory allocation. We can build entire worlds. I always think of that movie Inception. It's like, what do I want to build? Well, I can build millions of things, right? And so that's the really fun part about the heap is I can build whatever I want, and it is not going to go away at the end of these curly braces. It's like a giant playground where I can build worlds out here. And as long as I have one pointer to one part of that world, I can hand that pointer around and it's never going to go away. The stuff on the heap is going to stick around until our program stops running. Okay. So the heap is like a really fun place, and most really interesting code ends up creating lots and lots of stuff like web pages or 3D games or geometry. All of that stuff is being created on the heap very dynamically based on information in a file or maybe stuff that comes in from the internet. There's lots of ways that that might happen. Now, many of us have experienced old, slow computers. And what happens is sometimes you got too many things running in memory, too many web pages, or you got Photoshop, or you got some 3D program or some movie playing. We run out of memory, and heap memory starts spilling over onto our slower disk. We use that disk as like an emergency place to put stuff if we make too much stuff. Now we got really nice new modern computers. We got tons of memory and everything's fast and feels good. But when it starts bogging down, a lot of times it's because we've run out of memory and it's now starting to read and write, almost like it's reading and writing a file, quite literally, to hold on to stuff that it can't keep in memory. It's like having a piece of scratch pad you got to go to every time you run out of memory. So it's not a good thing. We don't want to go there, but that's just another way that memory is dealt with. Now, there's a few corner cases, weird things like const char star text equals hello world. Weird variables like that are read only. We're not allowed to reach in and change that O in hello world to something else. So we call that the data segment area of memory. And there's similar things like this that we just initialize when we start up with our code, but we can never change them again later on. So I can't go in and change that particular thing later on. Okay. And then we'll learn about this area called static memory later. Okay. But our main focus is going to be this heap area over here, because that's where most of the fun stuff actually happens. Okay. So we're going to dig into that. And the thing to remember is that whenever we are wondering, did I create something dynamically or not? Well, certainly on my slides, if it's in blue and it's got a name, well, that's not dynamic, that's automatic. And it's going to live generally between two curly braces. Okay, so int val or char s10, those are just named variables that are going to go away once we leave the particular scope they were created in. If you see the keyword new, that means we're creating something new on the heap. And I'll try to color these things orange to help us kind of as a clue in my slides. So that means there's a new integer. New always, always, always gives us a pointer. New returns a pointer. So that means if I'm going to hold on to that integer, I have to put its address over here in some variable. Okay. And it turns out that this variable is going to, in this case, just be one of my automatic variables. So int ptr is a pointer to an integer. Okay, so int star, and I've called it int ptr. Obviously, you could call it anything you want, but that's us holding on to a dynamically allocated integer that's floating out there on that Wild West territory called the heap over there. Now, similarly, I could create lots of things. So I could create new characters, and I can create 10 of those things. And now I got 10 characters in a row that I created just right now. I'm holding on to the address of the very first one. So people would say, wait, that's an array, but this is a character pointer. Well, turns out that arrays are just pointing to the first thing in the array. And then we just play hopscotch to find the next thing and the next thing and the next thing from the first position. So it really is true that a char star variable is pretty similar to an array of characters. And so we can hold on to the first address of 10 characters and then treat that thing like a dynamic array later on. And we'll see some code that will actually do that for us. So that's our main focus. The static stuff we'll come back to in a little while. We won't go too much into that, but it sticks around also for a really long time, but it has some other interesting applications we'll see, okay? The most important use of our statics is going to be inside of classes. So we'll come back to that and use our statics inside of our classes. That's really mostly where I think things are the most interesting. But let's go back and review our automatic allocation stuff. So here's my imaginary area called the stack. That's where all of the blue variables are going to go, right? So if I say for int I equals 0 to less than 1,000, and I create this variable, I'm sort of ignoring I for the moment, but if I say inside of that for loop, what's going on there? Well, it turns out that it's going to create cptr loop. I'm not doing anything with it. It's a uninitialized pointer or address, but every time I loop around, it goes away. So it's going to go away and come back and go away and come back every time I loop around, which might be a surprise to you. But a for loop is special that way. Those curly braces get created and eliminated on every loop iteration. So that's why if we try to put a counter inside of a for loop, it always really gets set to 0 every time. We can't really increment it inside of the for loop. We got to create some sum variable out here, and then we can increment it inside, right? So anything that's created inside of the loop goes away at the end of that scope, okay? So again, just to emphasize that, that whole thing is like creating, deleting, creating, deleting, creating, deleting automatically, which is why we call that the automatic allocation. Okay, so we obviously can't access CPTR after that for loop, even if it was interesting to do so, right? Because it's gone, right? Once we're out of there. But the good news is we haven't leaked any memory. We didn't leave stuff hanging around anywhere. It gets automatically cleaned up. So that's a really nice thing. So scope tells us when something is created and deleted or deallocated. Even in main, when we create something like that, right? And then we do something inside of that, right? There's the B, there's me. Now, this is a bug. I'll show you this bug. So notice what's going on here. There's my A pointer. I haven't done anything with it yet. Now, inside of this for loop, I'm going to create a B, and I'm going to do a very bad thing here. I'm going to steal the address of the B, and I'm going to store it in A pointer. So this is very bad coding, and maybe some compilers will pick it up, but many of them won't. So I'm holding the address of the B up here. So in a sense, I'm pointing to the B using this variable as if I'm going to access it later on, okay? And I could do all sorts of other things. I could create an array over there. But once that for loop is gone, right, at the end of that scope, all the variables created inside of there go away. But guess what? A is still pointing to this area of memory as if it's still there, okay? And yes, the transistors are still there. They didn't magically go away, but someone else is using them now. And so if I access that area of memory down here, it is very likely that I'm going to get garbage data, or worse yet, I might crash my program. Okay. So this is an example of a very dangerous way to steal or borrow the address of something that's not going to hang around for a while. And so a lot of really nasty bugs get created this way, where we grab onto a pointer using something out here that has a longer lifespan than this scope right here, okay? So that's one really important insight as we start working with dynamic memory or pointers. We want to understand, hey, is the pointer that I got going to live on? Like, does it point to some memory that's volatile, it's going to go away, or is it safe to actually keep hanging on to that? Okay. And so this would be a bad example here of how we would write that code. Okay. Now, as it turns out, there's nothing really magical about the for loop that creates that scope. Any two pair of curly brackets creates temporary scope. So this is one thing that I didn't know for a very long time about C++. If you want to create a little temporary neighborhood where things are useful and then they go away, all you got to do is wrap them inside of some curly braces. This is a really good trick. So for some of you who look at my test me code that I write, I'll usually like create a bunch of variables and, do some stuff. And then I know for sure that it's all going to go away after this, so I can use the same name later on, right? Because I'll copy paste a lot of code. So it's just a little trick for me to create a safe region where nothing in here is going to collide with anything in some other neighborhood, right? So just something you can do, but the rules still apply. Once we get beyond this place, we can no longer access the memory that was allocated inside of there, because it's given back to the system and it's going to be used for something else. Okay. So those are kind of the ground rules for working with these blue kind of automatically allocated things. Okay. Hide that guy right there. So now let's move over to us creating things over on this heap thing. Okay. So I can have a named variable that holds on to the address of something over here, right? So here's me creating a place to hold on to. Think of it as the tip of the iceberg, or use our fishing pole analogy. I'm going to be casting a fishing pole into the heap ocean, right? So if I say IPTR equals new int, IPTR is a pointer to an integer. New always gives us a pointer to whatever it just created and puts the pointer over there. So what we're really saying is the I pointer variable up here is holding on to the address of this thing down here. So I pointer is pointing to a chunk of memory, okay? I pointer is not the chunk of memory. This is the chunk of memory. I pointer is just a place where we write down its address, okay? So here is an unused pointer to a character. We haven't created a character yet. This is not a character. This is a pointer to a character, okay? So if you really want to simplify, just think of it that way. It's a pointer. It's a 64-bit variable. What kind of variable? It's a pointer to a character, right? So it's the address of some character. So now I can say something like this. I'm going to create 5 new characters all in a block. So this is the syntax we use to create a bunch of characters. And we get the pointer to the first one and we store it in that variable. So new always returns a pointer, okay? So new gets the pointer to this one right here. And later on, we can then play hopscotch and jump from place to place to place using our square bracket format. Okay. So if we don't know how many things we're going to have to read from a file until we open the file, we would use dynamic memory. We'd say, well, let's read the first line of the file. And it says, oh, there's 5,000 words here. Okay, well, we'll create an array with 5,000 pointers to some string variable, for example, right? So that is the situation where we might use these dynamic things. But eventually, when we're all done, we want to come up and clean up this memory, right? Because this is not going to go away. So I've used this analogy before. If you're playing a video game and you're done with one level and you want to load another one, but it sort of gets slower and slower the more levels you switch between, that means your video game has a leak. It's not cleaning up all of these dynamic allocations. Same for the Chrome browser. If you go to a new web page and a new web page and you're like me, I don't like close Chrome for a month at a time, and it slowly gets slower and slower, that's because it's probably not freeing up all of its memory. So at some point when you're done with the memory, you've got to clean it up, right? So if I say delete I pointer, that means delete what I am pointing to. Notice I'm not deleting this. This was very confusing to me for a long time. Delete I pointer looks like I'd be deleting this, but I'm not. Delete says follow the address here of what it points to and get rid of that thing. Okay. That's what delete is doing. These things only go away when they go out of scope. Okay. So delete what I pointer is pointing to, delete what the C array is pointing to, and give it a little extra hint that says, hey, by the way, that thing's an array. You better delete all of those things, okay? Not just the first one. Now, if you ask me, C++ should know that this is pointing to a whole bunch of things. It should sort of have some table lookup where it knows. But we have to tell it to delete all of them by giving it a pair of square brackets. That's an unfortunate syntax requirement, often gets forgotten and creates some terrible problems. Okay. Now, once we do this, C pointer, C array, and I pointer are pointing to nothing, or they've been reallocated. So if we try to go poke around in that memory using these two things, we're going to get in trouble. We might crash our program. Someone else might be using that chunk of memory now. And so trying to make changes to it via these pointers could cause some very, very bad things. So C++ is very dangerous in that way, where if you don't realize that those are no longer valid areas of memory, you could stomp all over some other part of your program. So it's a very good idea to nullify these pointers, set them to null PTR, so you don't accidentally go mucking around in that memory, okay? We still haven't gotten rid of the stack variables IPTR or C array. Those will automatically go away whenever we get outside of some curly braces scope inside of our code. Okay. Questions on any of that stuff there? Okay. Well, we'll look at more examples of this as we go, but these are the key pieces. So come back to these couple slides if you kind of go home and stuff doesn't sink in. Let's look at some more risky pieces of code. Here's a for loop where we do something like that. Inside of the for loop, we create a pointer and we say, oh, I'm going to create a dynamically new allocated character. Okay. So this is a pointer to a character. this is a character, but new always grabs the address of that character and gives it back to us. So that is apples and apples, character pointer, right? So now we're hooked up, okay? But because of what we learned a few slides back, look what happens every time we go around the loop. We go around the loop, we lose CPTR loop, but we don't get rid of that other piece of memory, okay? Heap memory does not automatically go away. It's not automatic. So now we just have created a leak and another leak, another leak, another leak. And so when our loop finishes, yes, CPTR goes away, but all of that memory we allocated is no longer available and we can't even go find it to clean it up. So the only way to clean up that memory in C++ is to stop the program and start it over again. That's like shutting off your game or crashing your browser or shutting down a server. So those are very volatile things to do. So we obviously don't want code leaking memory like this, okay? We're kind of stuck and we need to avoid that situation if we can. So although this is kind of silly code, right? This is something that would be safe, right? So we do allocate something, we hook it up. We can do that all in one line, right? This gets the address of that, right? And then we delete that. So, but we're not deleting this. We're deleting what it points to. That's the key thing about delete. It's going to delete what this thing is pointing to, okay? So, and then the automatic allocation of the stack will get rid of CPTR and then recreate it on every single loop. So although I didn't animate that part of it, both of those things are being destroyed and created on every loop iteration, okay? Doesn't do anything useful, but eventually that thing will go away and there's no wasted memory, okay? So kind of a silly piece of code, but it shows you pretty clearly pretty literally what's going on underneath the surface when we write code like that, okay? So if we create with a new, we must delete with a delete, okay? That's the moral of the story. For every one of these, there must be one of those, okay? And we only need to delete things that are pointed to by some address, okay? So notice that delete does not delete this. That goes away because of our curly brace, okay? So now let's see if we can do something a little bit more useful. So let's say we want to dynamically allocate 9 pointers to integers, okay? So this is an array of 9 pointers. Where do they point to? Integers, okay? So there is an array of 9 pointers. Now, they don't point to anything yet. They're all probably garbage or zero or null. We really don't know. We shouldn't assume. Okay, but now we can loop through them and create little chunks of memory, right? So now I'm creating one integer and another integer and another integer. I really should have had my arrows like better drawn here, but I just got a little bit lazy with my animation. But that's my idea there. It's like as I loop through those 9 things, I'm creating 9 little blobs on the heap and hooking them up. And this is the way dynamic data structures are created. Many very, very exotic ones. If you think of 3D geometry or Facebook or anything where there's a lot of things connected to other things, those are usually managed by pointers, okay? So here we've created an array outside of the for loop and then dynamically allocated little chunks of memory. And we can come back later on and delete that memory, right? So here, take a look at what I'm doing here. I'm saying delete the pointer, what I points to. So if I is 0, I'm saying delete this. When I is 1, I'm saying delete this, okay? So I'm saying delete I PTR array sub bracket I, okay? Go to the ith pointer, find what it points to on the heap and delete that thing, okay? So now we're cleaning up that memory, okay? And then in this case, again, because of the outer scope, right, then our eye pointer is going to automatically go away. Okay. Now you might be thinking, can I put the whole thing over here? Could I just have that whole thing over here? Yeah, we could totally do that. But we're just kind of starting out a little more slow and doing that over here on the stack. Okay. So it's a little bit hybrid. Part of our data structure is over on the heap or on the stack. Part of it is over on the heap. Okay. But in that particular case, we have no leaks. Okay. So let's take a look again at what's so bad about leaks, right? So if I were to just have a runaway thing like this 1,000 times, eventually it's going to fill up my memory, and hopefully the operating system is going to stop this and say, hey, hold on there. You know, stop doing that. I'm going to kill your process. But if this was like the Mars rover on Mars, there's no operating system there, maybe necessarily to overwatch what's going on, and we could end up crashing that device. So C++ gets used on a lot of things like drones, self-driving cars, stuff like that. And there's not this wonderful Windows, Mac OS operating system watching over everything all the time. So in a situation like this, it could totally take down the entire system. Okay. So we grind to a halt, we crash, nothing can actually happen. Okay. Let's take a look at a couple other examples. Why would this thing be leaking memory, or does it leak memory? So there is a blue variable name. It's got a name. That's a big clue. There's no new word there. So that means we're not creating anything new on the heap. So there's no orange stuff. So really, we're not leaking any memory at all. Okay. We're just creating and getting rid of that CPTR loop on every loop iteration. Okay. So that's okay. Okay. Over here, there's a pointer to a new array, right? All over on the heap. So CPTR is pointing to just the first 0th location. So in a sense, that means add 0 memory to the address to get to what's there, right? If I added 1 integer, that means hop over 1 integer. If I said 2, hop over 2. So you can kind of see how arrays work. They just sort of skip over, sorry, not integers, characters. They play hopscotch based on the type of data they're storing there, right? So there's my 9 things. But here, look what I did. I forgot to put in the square brackets there, okay? And we could all be forgiven for getting to do that. But that leads to a very nasty bug, unfortunately. It destabilizes your code in ways that is very hard to debug, okay? So heads up for that. If you create it with square brackets, you're going to need to delete it with square brackets, okay? So remember to keep those things in there. If you see them up here, they should be down there as well. Okay. So let's take a look at another one, just a couple more of these. So I have a stack variable pointing to a little character over on the heap. I delete what it points to, right? So that thing goes away. And really, this is okay. I should have also put my curly braces in there too. So you could see that not only does the orange thing go away, but the CPTR goes away at the end as well. Okay. So that is okay. Okay. And then maybe the last one here. Here's me creating a new character. So this happens a lot. So I create a bunch of new characters and then I reuse CPTR to create another one. But watch what happens there. I've completely lost control of that chunk of memory over there, and there's no way to get back to it. So there's really no easy way to go erase that stuff. Okay. So if I delete CPTR, the only thing I'm deleting is what it's pointing to now. And now I have a memory leak. So when we have languages like Python or JavaScript or Java, they have something called a garbage collector that's always watching. And if it sees that no one cares about this anymore, it will automatically make it go away. So garbage collectors are always watching to make sure that any memory that's floating around the heap has at least one pointer pointing to it. So in languages like Java and Python, if that chunk of memory over there is no longer cared for by anyone, then the garbage collector just picks it up and returns it to the pool of available memory. C++ does not have a garbage collector, and so we have to be the garbage collector for that stuff. Okay. So whenever we use new, we need to use delete. Okay. So clean up your own stuff, right? If there's a new, there should be a corresponding delete. If you create new with square brackets, you should delete with the square brackets. Sometimes these two pieces of code will be thousands and thousands of lines apart, or millions in some extreme cases. So it can be hard to figure out where and when it's time to clean up a piece of memory. Okay. Remember also that whenever you use new, you get a pointer, no matter what, always, always, always. And whenever you use delete, delete needs to be given a pointer. You can't delete an integer with delete. You can delete a pointer to an integer, but you can't delete the integer. I mean, delete will go delete the integer, but you have to tell it where it is by giving it a pointer, okay? So those are kind of the holy grail things you got to keep charge of, okay? So if you try to delete something that's not a pointer, you're going to get a crash, pretty much. Okay. So let's take a look at some of our 4 examples, right? So here's an array, a dynamic array of integers. So we've kind of seen this before. So here, it looks like it's a pointer. Pointer to what? It's a pointer to an integer, okay? Well, that's another name for an array, right? So I can say my array equals new int of size, and now I've just created a integer array with 4 items in it. So I've dynamically created an array. And for pretty much most reasons, it's identical to an array, right? And I can come back later now and dynamically delete that array. So if you don't know how big your array needs to be, this would be how you would go about actually creating it rather than just taking a guess, okay? Rather than saying int my array 100, this is how people used to write code. And then if somebody goes beyond 100, we crash our program. Now we can just ask the user like, hey, how many do you want? I need 4. Okay, let's create 4 of those things, okay? And then later on, we can get rid of that stuff. Now, again, don't do this. That will crash your program or destabilize things pretty badly. And this is a good idea. It's a good idea to set that thing to null so that nobody accidentally uses that pointer. Okay. So that's a one-dimensional dynamic array. Okay. Now here's a couple things that are hard to realize unless you see them all on one page. We've kind of seen this before, right? We've seen this before. So we're just sort of initializing that thing. Here we're leaving out the size and letting these things kind of initialize that. So we've seen that before, okay? Now if we do it this way, right? Or this way, that's okay, but we cannot, you know, this is terrible. We can't use an equal sign there. Otherwise, we'll get a compiler error, okay? Makes me a little bit crazy. So, but if you are trying to do that with dynamic memory, you might think, oh, I can't, it's not supported, but we just got to take out that equals sign, okay? And then this one's real secret sauce. I'm not going to test you on any of this stuff, but some of you might be interested. How do I make sure all these things are zeros? Add a pair of parentheses. Who knew, right? Like that's a pretty hidden little feature. So that will ensure that our dynamic array has all zeros in it. That can save you a lot of time, okay? So there are all sorts of little corner cases. Here's me initializing a dynamic string to hello world and such. But we cannot use our brand new range-based for loop to loop through dynamically allocated things. That's one big drawback to dynamic allocation. We can't use this dynamic memory looping thing, okay? Or the range-based looping, okay? So just a little bit of, you know, extra sauce on the side. I'm not going to test you on this, but it might simplify some of your homework coding down the road. Okay. Okay, so let's take a look at 4 different exercises to solve the same problem in 4 different ways. So if we ask a user, how many numbers would you like to add together? And they say, I'm going to give you 3 numbers. Okay, now we can dynamically allocate some data structure. We can collect those numbers. We can add them up, right? And from some local dynamic memory, print out the sum, and then delete those structures, right? So once we've, printed out the sum, we don't need the data structure anymore. So that's what we want to do, and we want to do it in 4 different ways. So I'm going to show you 4 ways. Some of you probably remember this, but the idea is the first way is just going to be a dynamically allocated array of integers. That's pretty much the most obvious way we would do this. But we could also do it this way. I could have an array of pointers which indirectly point to integers. Seems like a waste of time, but we can do that. We can have a pointer in the array, which means that this array is actually a pointer to an integer. Okay, so let's review that. This is a pointer to an integer. Okay, pointer to an integer. This up here is just the array is a pointer to an integer. Okay, so remember often we read the data type from right to left, pointer to an integer or pointer to an integer. Double pointers make people crazy in C++, okay? And triple pointers make them even crazier. Okay, so we'll try to demystify this for you. Okay, but that's about as complicated as it's going to get in this class. Okay. But we could, in addition to putting integers in here, there's nothing that stops us from putting an entire instance of a class in there. So let's say we had a class called num, right? That was a wrapper around an integer or a number. Now I can store instances of numbers in there, right? Now, what's actually in there when I do this, right? If I say my array equals some number of instances of num, it's just going to call the default constructor and have an entire instance of one of these classes in every array position. So we'll look at some examples of that here before we get to the end of class today. Okay. So you can kind of see that this and this are pretty similar, right? Pointer to some data type, pointer some data type. And then 4 is, again, kind of like the second example. We have an array of pointers to an instance of a class, right? So my array is a pointer to an instance. My array is a pointer to an instance. Okay. So those are our 4 examples. So this lecture, is good, reference material to come back to at any time. You can get out of most problem situations with this kind of stuff. But let's dig into the first one. I've kind of seen this before. I'll try to live code, but I always suggest you guys try this along with me. But we're just going to try to create an array based on what the user tells us. So we know we need a pointer to an array of integers, right? We're going to ask the user how many things, and then we're going to allocate that thing, right? So let me jump on over into this. See if I can do it without losing everything. Refresh. And refresh again. There we go. Okay, so I'm going to skip past and just look for the to-dos, right? So how many numbers do you want? Notice that our array is a pointer to an integer. So it's just an array of integers we're going to allocate on the heap. So I'm going to say my array is equal to new, and I know it's going to be an int, and I need total numbers of those, okay? So notice I didn't put a star in there, right? Because new always gives me a pointer. So my array is getting a pointer to an integer, which is exactly what we want, okay? So now I've got that chunk of stuff on the heap, and now I'm going to loop through and collect something from the user, but now I need to put that TMP in the right location. So I can just say my array, square bracket, I gets temp. Okay, so I'm just treating it like, TMP, just treating it like a regular array from now on. Okay. And now if I want to go through here and add up things, once again, I can just say sum plus equals my array of I. So you see, I'm really just treating it like an array, even though it's a pointer to an integer. Okay. That's really all an array is. Okay. And now down below, after I've calculated the sum and printed this out, we're going to go ahead and delete the whole thing. So I'm just going to say delete. And I don't need to loop through in this case and delete anything using a loop. I just say delete my array, but I have to put those square brackets in there. Okay. My array to remind it to get rid of all of those integers, right? New with square brackets, delete with square brackets, okay? And then for safety reasons, I just set that to a null, okay? So this should work without crashing, but it looks like I have missed a semicolon somewhere because of all my vacation time and Python coding. So let's see if I can get past that. May array, that's another little typo. Where's that line 46? There we go. Okay. And that should be the last one. There we go. So I can say 1, 2, 3. Oops. Let's see. How many would I like to add? 3. Right. Sorry, I wasn't following my own instructions. 3. Okay. First number is a 3, then a 4, then a 5. Okay. So notice that after the delete, before I set this thing to null, it's still pointing to the chunk of memory that I've already deleted. So that's the danger, right? My array at this point right here is still kind of a loaded gun. It's pointing at some memory that I should not be messing around with. So once I set it to null pointer, essentially that's the 0 address, okay, which is always reserved for the null pointer interpretation, okay? So sorry, I should have made that a little bit bigger so you can see all of that, but that's kind of what we're down to there, okay? So that is kind of the pattern we're going to follow with a few variations here. So I think we should be able to get us to 7 o'clock here without too much trouble. But this is the code that loads it up, sums it up, and then deletes that array. Okay. So that's kind of your basic bread and butter. But let's take it up a notch with these pointers to integers. So this is a little bit how we're going to do homework 5. Okay. So I'm going to use this friendly little elephant here to try to help everybody remember. So you should be worried about the elephant is the moral of the story. So if I have a variable that points to nothing so far, right? It's just an array double pointer. So it's going to point to a pointer, which is going to point to an integer, right? So I now, notice I put the star after the int. So I'm saying, give me an array of 4 integer pointers, okay? That's my ladder, okay? I haven't put the elephant on the ladder yet. Now there's the elephant. So I've said, go to position 1 and create an integer and store the pointer to that integer in the square bracket 1 position right here, okay? So now we've hooked up some integer value there. We still haven't put a value in there, right? So we don't have a value over here at all. We've just created space for that thing. So now here's the tricky part. Dereference the pointer at position 1 and put the 12 there, okay? So star myArray1 is like saying, go to the address at a particular variable. It just so happens that that address we're referring to is this one right here. So we're saying, go to what you're pointing to at position 1, not 0, right, but 1, and put a 12 at that location. Okay, star myArray1 equals 12. Okay, so now the elephant is number 12. Okay, now if I want to clean up my memory, this is my silly analogy. Don't delete the ladder until you delete the elephant, right? Otherwise, the elephant falls on the ground or becomes a memory leak, right? So we delete what's at location 1, right? Follow the pointer, delete the elephant, right? Then you can delete the ladder, okay? Okay, so when we create very complex data structures and build them up this way, we sort of tear them down in reverse. So we build a ladder, put the elephant on the ladder, and then when we undo it, we got to do it in the reverse order. Otherwise, we have memory leaks all over the place. And so this will be a constant sort of reminder for you for your homework 5, and your homework 6, and your homework 7. If you build it up one way, you got to tear it down in reverse. Okay, otherwise we'll lose access to our memory. So let's see if we can do this one together too, right? So same kind of question, but we're going to dynamically create this little piece of indirection here, okay? So, and then we'll tear that thing down, right? But we're gonna need a loop this time to tear down, get rid of the elephants, right? So these are all the little elephants. And then we're gonna get rid of the final array last, okay? So let's see if we can do this dynamically together, okay? Or you can at least watch, right? So let's go down to the to-dos, okay? So notice that my array or my ladder is a pointer to an integer. So there's a little indirection there, okay? So my array is equal to new int star total numbers, okay? Not a double star, right? Because I will get the double star from the new, okay? So in a ladder or an array of pointers, right? Loop through, get a number from the user, and then say, go to the location star my array at I and put temp in there, TMP, okay? If I try to put an integer in this array, the compiler would say, hey, that's not the same thing, right? So I have to say follow the pointer at I and put the temp there, okay? And then down below, we can just say sum plus equals my array square bracket I, but we have to dereference it and say go get what it points to, right? Otherwise, we're trying to add a pointer to an integer, right? That's an integer, that's a pointer. Dereference gets me the integer, okay? So we're following the arrow to the elephant, right? Okay, so that's all going to happen inside of here, right? We don't want to delete anything, right? Oh, actually, so once we've deleted this, or once we've summed it up, let's take a shortcut and we'll say, well, I'm done with you now, so I'm going to delete my array of I. So I'm saying, get rid of the elephant that we're pointing to, okay? Don't use the star on that one, just follow the pointer. I know this is very confusing, these two things here. There we have to follow the pointer to get to the number. Here we just feed it the pointer and it will go follow the pointer and delete it for us. Okay? So we add it, we clean it up all inside of the loop. And now we can go ahead and delete the ladder, right? So we can say delete my array. Ah, but I need my square brackets because it's an array, right? Like so. Now I could have had 2 for loops, one for the summing and one for the deleting, but I just sort of combined them into one for loop, okay? So let's see if it actually works. Okay, I'm gonna say 3 numbers, 3, 3, 1, 1, 4, 4. Whoops, what did I do wrong here? How many would I like? 4 numbers. Okay, enter a number, 3, 3. Oh, something's wrong. Here, let's see if we can spot it. How many numbers would you like to add? This is a good one. Total numbers. My array. All right. New int total numbers. I know what I didn't do. This is pretty good. So I never created the elephant, right? So it says create space for one integer, right? So, but I never did that. Here's what I was missing. My array at I should be equal to a new int. So that's the elephant, okay? So I never created the space and initialized that pointer. And so it was trying to put something at 0, right? Okay, so that was a good learning moment, I suppose, but let's try this again. Three numbers, 11, 22, 33. Now that should be 66. Okay, much better. Okay. So that's a little tricky. Here's the solution for all that code. That's pretty much what we did there. Okay. And I had forgotten this key part right here, right? Forgot to create the elephant, right? So practice 1 and 2 are exactly the same as practice 3 and 4. We're just going to swap out int for a class. Okay. So if you're feeling a little bit overwhelmed, just sort of step back and just take some comfort in knowing if you understand 1 and 2, you already understand 3 and 4. I'm just going to show you that we don't have to stick with an int. We could go with any instance of any class, right? So whether it's integers or a num class, which is what we're going to do. So bear with me while I take you through this last two examples. So dynamic arrays of instances, 3 of 4 examples, right? So here's our class. It's just a simple wrapper around an integer. And it's got a constructor, and it's got a default value, which means it's a default constructor. So that means the array can automatically default construct all of the little values for us without us telling it what goes in there. They're all going to be zeros until I change it, but at least it can default construct. So I can say num n of 10, or I could just say num n, and it would be fine. Okay. So this is what we want to do. I want to say my array equals a new 4 instances of the num class. So we're literally going to have num instances inside of each one of these. No pointers to a num instance. They're just going to be instances inside of this dynamic heap, okay, or array of heap. So it's an array of instances. And then I can come back and delete them later on. Okay. So it's just like example number 1. Okay. So let's see if we can do this one. We'll do a live code on this one again. So we're going to do something like that, right? And we have to have a default constructor, okay? So let me see if I can do this and get it right the first time here. See if I can land this at 7 o'clock. Okay. Come on. There we go. Okay. All right. So there's my class default constructor. Here's a default constructor there. I did a little differently here. I have 2 constructors, but same result. That's a default constructor. So I'm going to allocate my instances. So I'm going to say my array equals new num4. Okay. So this is an instance, 4 instances, and this is the pointer to the 0th instance that's going to get stored there. Okay. All right. And then we'll load our numbers. Now watch what happens. Here's the integer value, but I got to get that inside of my array. So I'm going to say my array square bracket I dot. So I is an instance. So dot what? Dot, where'd it go? Value. And it's public. Okay. So I can say my array dot value equals TMP. Okay. So I'm shoving it into the instance at the particular data member of the class, okay? And now I can go through and add them up. So I can say, okay, now I want my array square bracket I dot value, oops, sorry, sum plus equals my array square bracket value I. So we're adding them up. Report out the sum, and then let's go ahead and delete. So we just literally say delete my array, and the whole thing goes away. Okay. So let's see if I get lucky on that one. My array using its value data member. My array equals temp assigned. Error expected semicolon. Again, missing my semicolons. Sorry about that, guys. Too much Python this week so far and not enough C++. Okay, so I want 3 things, 11, 22, 33, 66, okay? Okay, and our solutions here if you need it. Okay. So there's just the hint, but you can kind of skip forward to the final set of code if you need it. Okay, all that stuff is there. Okay, last one, and then we'll get you out of here. Okay, so here we're going to take one more indirection. So we're going to have an array of pointers to numbers. That's going to go into an array that has pointers to numbers. Okay, so this is a pointer to a pointer, which will point to a number. Okay, and so we could put a new dynamically allocated instance, and we can use its constructor now to give it an initial value if we want. So new gives us a pointer. That pointer goes into position 1 right here, and it points to the new instance of the num class. Okay. So that's our little elephant there. Okay. And then we can come back and delete that thing, and then we can delete the whole thing. That's the ladder. So here's our elephant. This is my ChatGPT picture of the day. Scared little elephant we need to get rid of before we delete the ladder. Okay. So there's our ladder, right? There's going to be our loop that's going to allocate those things for us. Okay. And then we'll clean that thing up. Okay, so let's see if we can actually do that one. So let me click into this and then we'll get you guys. No, I didn't want to do that. Okay, I'll have to restart the share. Sorry. Keep. Bear with me 1 second. Get back to our last example right here. Current slide and share. Am I sharing? What am I sharing? Yes. Okay, good. So we're over on the other slide there. Oh, I think I might need to, let me just make sure I am resharing control this guy. Good. All right. Okay. So let's go back to our slides over here, jump into our last example. Okay, so let me go to our to-dos. Okay. So here's our array. It's a pointer to numbers. Okay. Let's allocate some pointers. Okay. So I'm going to say my array equals new num star square bracket total numbers. Okay. So those are pointers to num instances, which I have not yet created. Okay. So I got to create them down here. Create a dynamic instance of a num. Okay. So I'm going to say, this is a little different. My array square bracket I equals new num TMP. So I'm passing TMP to the constructor of num. It's being created on the heap, and the pointer is going directly into the I pointer of the array. Okay. So that's me loading up all those numbers into my newly constructed instance of the number. And now I'll go down here and try to add them up. So I'll say sum plus equals my array square bracket I dot arrow value. Remember the arrow? If I have a pointer to an instance and I want to access a data member, I can use a arrow, not a dot. Okay. Okay, we're almost there. So that's us adding up. And now we can go ahead and, oh, and we forgot to delete. After we add, we'll just say delete what my array I points to. Okay. So that gets rid of the elephant. And now we'll get rid of the whole ladder. Delete my array. Okay. And don't forget the square brackets. Okay. And it would even be a good idea just to say my array equals null PTR. Okay. See if I got it. Again with the semicolon. Okay. I don't blame anybody for forgetting the semicolon. Okay. Again, 3, 11, 22, 33, 66. Okay. So 4 examples, right? All a little bit different. Okay. Some of them a little overkill. Okay. But essentially taking us on a tour of pretty much the major ways that we would be using dynamic memory for the rest of the semester. And this way right here is very much how we're going to do homework 5. So when you get to homework 5, bookmark this little solution right here. This will help you with your constructor when you're loading up puzzle pieces. Because very much when we load up a puzzle, instead of these number instances, think of us as loading up puzzle pieces, right? You open a box of puzzle pieces and you're going to load each one of them up and hang them off of these pointers so you can figure out where they go in your puzzle, okay? So we'll be doing some of that here pretty quick in homework 5, okay? So that's what we got today. Now, I realize there's a ton of new syntax here. And so if you have the time, Quizlet will be your friend for a lot of things between now and the end of the semester. So if we were to jump over to Quizlet, let me see if it'll let me actually do that. I don't want to log in right now. So let me use some of my, you guys may need to log into Quizlet to do that, create an account, but it's free. But let me show you what it looks like. You do not have to join the class. If you don't want to, you can just, these are open to the public as long as you have a Quizlet account or an app on your phone, which is really useful. But the question is, how do I delete this particular variable? Or can I, right? Is it possible to delete something here? And the answer here is we cannot delete, right? This is a const. And although we haven't talked about it yet, we actually can't delete constant things. They're constant, okay? So that would be a can't delete that thing, right? So here's another example. If you were to write this down in write mode, but you don't have to do write mode, but you would just write cannot delete, right? There's no new there, so I can't delete anything if there's no new, okay? Okay, so here is another one. Char C is a pointer to a newly created character initialized to the character X. So we haven't seen this before. We can treat the character variable type as a constructor and give it an initial value, which is pretty cool. So if I want to delete that, I'm just going to delete C, right? That says delete what C points to, okay? So that would be the correct answer there, okay? So you'll see more of these examples. They're really good to practice if you get the time. And the good news is you got lots of time, but they will be on quiz 5. So you might find that helpful. Okay. Okay, so lab today, I'll get you through this. It's a little bit tricky, but it's really a very good lab to build your skills. So the idea is we want to build a triangular matrix. So here's our prototype. So make tri matrix. How many rows do we want? Okay. So the idea is I call this function and I get back a pointer to an integer. That is a two-dimensional kind of data structure. Okay, and I'll show you a picture of that. So if I were to prompt you and say, how many rows do you want in your triangular matrix? The first row would have a position in it, and we'll initialize that to 0 because that's the number of the row that we're starting on. And then we'll have 1, 2, 3, 4, 5, 6, 7, 8. So this is ideally what we want. Okay, that's our triangular matrix. Okay, so the way our data structure is going to look like is this. I'm going to need an array of pointers. I've just sort of turned it on its side. And the first pointer here is going to need to point to an array with just one thing. Oh, sorry, it's over here, the 0th pointer. Apologies for the color problem there. Let me clear up my ink. So the first one is going to point to an array of size 1. That's a pretty silly array, but that's what we want to do. And this is going to be an array of size 2, an array of size 3, array of size 4, array of size 5. So this is a triangular matrix. It looks really messy, but it's really easy now to just access it like a two-dimensional matrix, as long as you don't go out of bounds, okay? And I'll show you the code in main that's already written for you. But this is what your function should build, and it should return this pointer right here, right? So anybody else can use your triangular matrix, okay? Okay, so let's take a look at some code in main. But essentially, you're going to have a for loop that's going to go through after you create this, and it's going to have to create these arrays by changing that 1 to a 2 and a 3, etc. Okay. But it's a cool little data structure for sure. So here's how we test that thing, right? We ask our user how many rows. We have a pointer to an integer, okay? So we're going to call the function. We'll tell you how many rows we want, okay? And then I'm going to go through and try to initialize it without crashing, okay? So if this crashes, that means something's not right, okay? Um, Also, usually if you get something wrong, so, oh, this is me printing out the matrix, right? And then I already have written a function that's going to delete it. This is usually where your program will crash. Because if you did not properly allocate things here, then this will probably blow up when it tries to delete things, right? If we try to delete something that shouldn't be deleted, it's going to for sure crash your program, okay? So all you have to do is do that implementation of that particular function, and you should be good to go, right? New stuff, then delete stuff, okay? And I've got everything else taken care of inside of main, okay? And notice that the return type, of course, matches the type. So that's our apples and apples. Matrix equals get matrix, okay? So those two things should match, okay? So if you can do that one, that's pretty good, right? It's an exotic, small but exotic little data structure. So I'll leave you guys with that, and let me know if you have any questions on homework 4. Otherwise, I'll see everybody on Thursday. Thank you.